Well, thank you. The speaker's working, which is great since most of you are hanging out in that corner as far away from me as you can possibly get. It won't be that bad, I promise. Yes, I'll be talking today about a range of the research that we're doing in my group at UW-Madison. I'll start by just giving a quick overview of our program at UW-Madison. Madison is basically like Urbana-Champaign, as far as I can tell, except even colder. We do have lakes, which is pretty cool, so you can go on them when it freezes. We've been consistently ranked as one of the top 5 NE programs over the last 40 years, and we do have our own nuclear reactor, and we have a full sort of gamut of nuclear engineering, radiological sciences, research, pretty much as you do here, with strong links to the industry and labs. What I do in my group is looking at fission and fusion reactor design and sort of why I want to try and get the costs down, because I personally care really hard about wanting to get more nuclear volts on the grid so that we can do something about climate change. And I'm going to go over a few different projects we've been doing today. And yeah, I think Dr. Novak pretty much covered this, but before I came here, I spent 6 years working in nuclear consultancy projects in the UK, and UK is one of those places that's sort of small enough that you've got a bit of chance to do everything, but big enough that there's quite a few things going on. So I did a mix of work on utility projects, but also on R&D projects, and I've now been in Madison for 4 years and have about 15 students, so that's keeping me busy. And I also am a joint appointment at Argonne National Lab. So first topic I want to cover is looking at what can we do with existing light water reactors. So the motivation for this is there is renewed interest at the moment in trying to squeeze more power and more burn-up out of the existing fleet of reactors. A few years ago when I started at UW, there was this quite a sort of negative trend around nuclear power in the US. Gas prices were really low, and there wasn't a whole lot of interest in building new reactors, and we were seeing reactors fall off the fleet and get shut down. Now, there's been this big change since I got here, which is we're now seeing utilities talk seriously about increasing the amount of power they get out of their reactors. We've seen plans to restart units that have shut down, which is all really exciting, and that's linked partly to increasing energy prices and also due to political intervention like the Inflation Reduction Act. Now, if we want to squeeze more power out of an existing reactor, so the whole fleet at the moment are pressurized and boiling water reactors, one of the things we've got to think about is making sure that we can do so within safety limits of the fuel. And to sort of explain where we're going with this, I first need to just recap what a fuel assembly looked like, which hopefully a lot of you have seen. So in a pressurized water reactor, which I think is about 2/3 of the units in the US, they're made up about 1 to 200 of these things, which are very tall, very thin fuel assemblies. Each one contains about 260 pins in this regular grid, which is 17 pins down each side. And they have control rods in them that go into little tubes. So on this sort of plan view and assembly, you have tubes, and you would insert control rods that look like this into those tubes. So these hang above the core, and then you can insert these control rods into the tubes. And this thing here is colloquially known as a spider, and it's a piece of equipment that's already in the reactor and fits into these things. Now, if we want to get more power out of a nuclear fuel assembly, one way we could go about it is to increase the number of pins in the assembly. And that gives us more heat transfer area, which is good from a point of view of departure from nuclear boiling or critical heat flux. It makes it easier to get heat into the coolant without having problems with heating up the coolant. And the other thing is, if you split the same amount of power among a larger number of pins, it reduces the peak temperature in each of those fuel pins. So in principle, if we're able to put more pins in an assembly, it's one route or one part of a story towards managing to get more power out of that assembly. Now, this has been very commonly done in boiling water reactors. So boiling water reactor assemblies look like this thing on the bottom left here. They are in these square boxes, And inside of those boxes, when boiling water reactors first started operating, they had 49 pins per assembly, so 7 down each side. The assemblies are a bit smaller than those in PWRs. And then they increased the number of pins over time. So they went to 8 by 8s and then to 9 by 9 assemblies, and they started doing funky things like put water rods in the middle of these things. And now currently the fleet operates with something that looks more like that. It's a 10 by 10 assembly, so 10 pins on each side, and then these water rods in the middle. And even some designs of fuel have 11 by 11 pins. So the number of pins in boiling water reactor assemblies has kept rising. And this has helped get more power out of the assemblies and facilitate uprates in boiling water reactors. However, unlike in PWRs, while there hasn't been this same move, we're all still stuck with the 17 by 17 assemblies. That's pretty much what everyone does. There's been some academic studies that look at trying to have like 19 by 19 or 21 by 21 pins per assembly. That gives you more fuel pins. It gives you a route to more power. But it's not been done. And so the start of this research was trying to understand why hasn't it been done and what can we do about it. Now, the problem comes back to these spider assemblies. So these things go in specific locations in the core, and these are all but irreplaceable. The utilities really do not want to change out these because they're safety critical pieces of kit, and it'd be very expensive to get rid of it and change it for a new one. And the control rods go in specific locations. You can't move them. So that means we're stuck with our tubes being in the positions we showed a minute ago, which are these ones. We can't move those tubes. And those tubes are consistent with having 17 by 17 pins per assembly. However, we don't necessarily need to keep a square lattice. So, and this is what we're looking at UW. So if we depart from the implicit assumption in all of this that we need our pins to sit in regular grids, then when we can get more fuel pins into the assembly without having to change the spider. And so this is just one way of doing it. And the color of the pin here is just to do with how close it is to the neighboring pins. So we take our existing guide tube positions and we jam as many pins as possible into it in an irregular lattice. And this is heuristically done, but you could imagine optimizing that. And then the questions become, does this lead to hotspots in the pins? And also, does this lead to hotspots in the coolant? So these are the sort of things we need to check. And this is where computational modeling comes in. So existing computational methods are pretty good at telling us what the power peaking inside a fuel assembly is. So if we can set up a model using a radiation transport code, we can figure out what power peaking we expect in these pins. And on the left is our conventional assembly, and on the right is the new assembly design under consistent conditions. And here we use a Monte Carlo neutronics code called OpenMC, which was developed by MIT and Argonne to analyze this problem. And we find that we get about 2% higher power peaking with the one on the right compared to the one on the left. Now, that's quite a small difference. And it would be relatively easy to drop that difference by having a small enrichment zoning in this assembly. So if we really cared about that 2% extra power peaking, we could knock down the enrichment of a couple of these pins by a fraction of a percent and bring it back. And this one has 23% more pins in it than this one. So there is potential there for increasing power in the assembly by 20% without changing the peak pin power and maintaining the same departure from nucleate boiling ratio. Now, this isn't the only thing that goes into upgrading a PWR. There's a lot more to worry about than this. You have to worry about safety analysis. You've got to worry about the amount of fission products that are in the fuel and could get out in a hypothetical accident. And we've got to think about if you start increasing power by a lot, then you start having to do serious refurbishment of the plant. You need to start doing things like replace the turbine. But it is a route to doing it. So yeah, as I mentioned, you can, in principle, if we take these pins marked in purple here, then we could reduce the enrichment in those, and that would allow us to get back within the power peaking of the baseline assembly. The amount, there's a limit to how much we would like to zone an assembly, because It reduces the amount of life we can get out of the assembly if we've got less enriched fuel in it. But this is really quite a minor reduction. It's of the order of 0.2% just in these pins. So it will only have a very minor effect on the life of the fuel. And that would bring us back to in the same power peaking as the reference assembly. The next thing we need to think about is what happens if we burn the fuel up. So are these effects maintained if when we consider the fact of fuel depleting? And so we look at what happens to power peaking with respect to time with the fuel in the core, and we also look at what happens to K infinity with respect to time in the fuel. And the reference case is this sort of blue line here, and then what's happening with the variations on this 324 pin assemblies in the other colors. And what we see is that all of these effects are maintained with burn up. With these things, we are not changing anything about the hydrogen to heavy metal ratio of the fuel. So it's got the same amount of clad, the same amount of moderator. And so that means we get virtually no difference in how K infinity evolves with time. So this thing could be slotted into an existing core without that much change. Another thing to think about is coolant heat up. So if we have a non-uniform distribution of pins, this assembly has some pins that are rammed quite close together around here and here. So then there's a question about whether that would lead to unacceptable hotspots in the coolant coming out. And the method used here is a little bit more quasi empirical. So we use quite an old code to do a channel analysis of this, and that's where we break the coolant down into little blocks between all these pins and use some empirical correlations to estimate the heat up. So to do this properly requires something like a CFD analysis, but this is to try and get a first pass on whether this is an issue. And it turns out we get pretty much the same distribution in coolant temperature outlet from the fuel as a regular assembly, just distributed a little bit differently. So this is a method to pack more pins into an assembly. We've spoken to both the main fuel vendors in the US around this, Framatome and Westinghouse. The vibes I'm getting from the fuel vendors is that this is something that in principle can be done. You would need to do bundle thermal hydraulic testing on these assemblies to understand if to rederive things like departure from nuclear boiling limits, but that can be done, and it's something the industry does. Jamming all these fuel pins into unusual locations makes the fuel assembly more difficult to manufacture, but additive manufacturing is a route to doing that, so it can in principle be done. So our next step here is to look at the safety and thermal hydraulic aspects, and I'm collaborating with my colleagues at the moment on doing that in the coming years in a DOE-funded project. So that's the first thing I wanted to talk about. As I said earlier, I am cheating and covering more than one topic. So that's some of our work on existing reactors. Next up, I want to look at some of the things we can do with advanced reactors. Now, there's this huge buzz in the nuclear industry at the moment around developing all these different types of advanced nuclear reactors. And it's a really exciting time, right? There's dozens of startup firms saying, hey, we are going to commercialize our reactor technology. It's great. It will be cost competitive. It has all these unique, really cool features that make it cost competitive. And this is things like sodium-cooled fast reactors. We've seen TerraPower breaking ground on a project in Wyoming. There's high-temperature gas reactors, such as the one that's planned to be built here, molten salt reactors, and so on. Now, this is all great, but one of the things to recognize as nuclear engineers is nuclear does not have a good track record in the West at producing cost-competitive nuclear reactors in recent years. I think this is broadly well understood. I mean, so one recent project in the US is Votel, which is the construction of 2 reactors in Georgia, which went something like 3 times over budget and was a decade late. And this has been repeated around the Western world. Similar things in France, similar things in Finland, and the UK is repeating this at the moment and having a project going massively over budget. And there's a lot of work being done by the nuclear industry on understanding why this is. And it's been examined in many reports, which I totally recommend reading if you haven't already done so. And what it comes down to is civil construction. Nuclear reactors are essentially big civil engineering projects. They, like any mega project, then tend to get really late and over budget because the project becomes so complicated that it can't be managed effectively. So building a nuclear reactor is a bit like building a new high-speed train line or hosting the Olympics. It's really, really difficult to do that cost effectively. And the key factors that determine how your nuclear project goes are relate to how you are managing the project rather than what the technology is. So what does that mean for us as reactor designers, as researchers? If fundamentally we could come up with the best reactor technology we could think of, but then it would get stuck in building this massive civil engineering project that then becomes late. So one of the things we can think about there is what we're trying to achieve from capital cost reduction. So one thing we could do is try and increase the amount of inherent safety in the reactor, and that would mean we have less nuclear qualified components, and this is certainly a route that advanced reactor vendors are going down. And this allows us to denuclearize a lot of the plant. So one of the things that TerraPower are doing is separating their reactor island from their power conversion island. And the other thing is, can we do something to the design to reduce the cost of the civil engineering or construction? And that's what we're looking at in the context of high temperature reactors. So HDRs are TRISO fuel, so like particulate fuel, a bit like nuclear rocky road. You embed particulate fuel in a matrix, and they have a graphite moderator. And then they have gas coolant in them, typically helium. Now, the gas coolant means you have quite low power. You have very low power density. And what pretty much every HDR does is it ends up with a tall, thin core. And what's shown here is the XE100, the pebble bed reactor that is planned to be deployed by Dow. But fundamentally, they all look like this. You have coolant that goes up around the reactor, comes down through it, and then passes through this tube here into a heat exchanger. And by having a tall, thin core, it means that if you lose pressurization of your helium, all the heat conducts out of the sides, which is great because it makes the reactor very passively safe. However, it's also very tall. I mean, the X-energy reactor is like 9 meters tall, and that's common for any reactor that's producing reactor core for a HDR that's producing hundreds of megawatts or less. And if you've got this big tall core, you also need to then have a steam generator underneath it, and you have control rods that go on top of it. So nuclear reactors are shut down by holding control rods above the core, and they'll go into it. If you have an 8 meter tall core, you need an 8 meter tall control rod or something that's nearly 8 meters above it. Now, all reactors, or most reactor designs have two key accidents that they really, really care about and where most of the civil engineering costs come in. The first is that a reactor has to survive a direct hit from a jumbo jet, so aircraft crash incident. The second is that it needs to survive a very, very conservative earthquake. Now, the approach that a lot of reactor designers take to deal with this is to silo the reactor underground, and that means it is much less vulnerable to being hit by an aircraft. But then that gives you a very big hole in the ground, and you then start needing to worry about dewatering of that hole, and you also need to worry about earthquakes from the effect of earthquakes on having the reactor in the hole. So we end up with a big, expensive hole in the ground, right? The hole can be a significant chunk of the cost of the overall reactor. So if there is a way of getting that height down, then you can also reduce the cost of the reactor. Now, there's one way of doing that is being proposed by MIT, and they got some money from DOE to do it about 4 years ago now, which is to flip the entire reactor on its side and have a horizontal HDR. That's a really cool idea, and that's one way of approaching the problem. It has some downsides. You then have to start having horizontal steam generators and develop a whole load of new technology. So we're looking at another way. We're going to stick with the vertical configuration. And now the next piece of information we need here is to understand what's going on with these control rods. So go back to this slide one last time. Again, this is the XE100, the X-energy design. It has control rods that stick out the top in these tubes. This is part of the hide of the system. Now, those control rods are inserted through holes. Now, in XE100, they're inserted through holes in the reflector of a reactor. So what you see here is the edge of the reactor core, and then in a reflector, we have a hole, and we put the control rod in. In some designs of HGR, they might also put the control rods going through tubes inside the fuel elements. And the control rods, and I apologize, this picture isn't great. It's because it's come from an original reference of some of these designs. This is it on its side, and it has a annular absorber with 2 layers of boron and a hole in the middle, and the hole contains a cable which holds the control rod. And this boron is what in nuclear lingo, we'd say it's a black absorber. It absorbs any neutron that hits it. So it's got a big gap and in the middle of it, and the control rod already is knocking out any neutron that hits it. So this provides quite a bit of redundancy to have a telescoping control rod. So something that looks like this. So we have multiple stages that all nest inside each other. If we do that, then the whole thing can become shorter. And what the idea here is we knock out the top tubes on something like the XE100 and bring the whole size of it down. And so we have a project at the moment at UW where we designed this sliding mechanism. And so this was for students. They came up with this. And then we build a little prototype. And we are testing that prototype it's about this big. I should have brought it today. And we're testing that prototype at high temperatures. And we're also doing some modeling to think about whether it's still going to shut down the reactor. And this is a partnership with X-Energy, Framatome, which is another HGGR vendor, and also Idaho National Lab. So based on knocking out that height, we figured out that we needed 3 stages. We got an initial cost estimate from the industry saying that this could knock down anything up to 15 to 20% of the reactor capital costs. So this is a very expensive hole. It will not ultimately be this high. It will be much lower. I mean, we might end up in 5 to 10% if we're lucky, but it's still a means to try and knock down some of these costs. One other challenge we've got is XE100 is an online refueled reactor, so they would like this thing to operate for decades without refueling it. So if you're inserting this control rod into the core, you want to try and make sure that it will, as it absorbs neutrons, it will gradually lose its boron, and we need to make sure that it lasts for long enough as well. So yeah, here's a picture of our physical prototype. As you can see, to scale, it's pretty small, and we're confirming that we can drop it and it will extend properly. A couple of things we need to worry about is when we mount these stages inside each other, we need to make it so it doesn't rattle. So it needs to be tight enough so it doesn't rattle. But we also really can't have this thing sticking. And on top of that, it's got to keep doing it in a reactor environment, which is at like several hundred degrees C and in helium. And it will corrode a little bit because there are impurities in the helium, and they will have an effect at those temperatures. And so this is my colleague, Professor Coué, has a test rig set up where we have a furnace that takes it up to several hundred degrees, and then we stick the control rod inside it, and we are currently doing tests where we extend and withdraw it and see if it keeps doing that. And then we also need to think about the reactor physics. So as soon as we start jamming these stages inside each other, we need to make sure that it will shut down the reactor, right? That's the first thing a control rod needs to do, is provide enough work to shut down the reactor. The other phenomenon we need to worry about is in a pebble bed, you throw pebbles in the top and they get discharged from the bottom. And they'll be recirculated a few times. They'll go around maybe 6 times before they come out. But the pebbles at the top have lower burn-up than the pebbles at the bottom. And that means that there is a natural skew in the power towards the top of the reactor. There are also some subtleties with how the fresh core is loaded that can exaggerate that towards the beginning of life operation. Now, so one of the things we then need to worry about is ensuring that as we insert the control rod, the worth always goes up, i.e. the control rod, the more you stick it in, the lower the reactivity of the control rod is. Now, with a telescoping rod, this is not a given, because as you start to insert it, you have multiple stages of the rod that all hang together in this region where there's high power. As it continues to extend, you are moving absorbing material away from this red region into that green region. So it is plausible that you could have a control rod that the more you inserted it beyond a certain point, the less worth you'd get. And that would become tricky to control. There's probably ways around it, but it's something that we care about. So in order to the next thing we need to do then is build a reactor physics model to understand how this behaves. And again, we reached to Monte Carlo codes, and we've been using a mix of OpenMC and the Finnish code called Serpent to do this. If we're looking at a prismatic reactor, those things are relatively straightforward to model, but there are some challenges because we have these little embedded TRISO particles inside of this matrix, so that's one thing we need to worry about. This is a typical prismatic core that has a set of fuel assemblies that contain TRISO fuel. These circles are where control rods go in, and then it can have a central reflector, which is this white bit, along with a radial reflector. So this is a top view. Pebble bed, you see a few pictures on the right. Sorry, these are superimposed and probably shouldn't be. So in a pebble bed, we have pebbles that move down through the core, and the ones on the outside will move slower than the ones in the middle as they're loaded from the top. And the pebbles have a random distribution. We don't know where they all are as they keep getting dropped in. So in order to understand the worth of the control rod, we need to understand roughly what the burn up in all of these pebbles are so we can calculate the power distribution so that we can understand the control rod worth. And that's a very difficult modeling challenge, and that's something our students have been doing working with Idaho. So what we find when we do all this is that we can, in principle, get a worth that's pretty similar to that of a conventional rod, and that's shown in the bottom left here. So conventional rod's this line on the top, the telescopic one is a little bit lower. And this is driven by that middle stage of a telescoping rod. It's a bit too thin, and as a result, it can't quite absorb as many neutrons. A lot of neutrons will miss it, and so it's not quite as high. However, another interesting feature when we dug into it, for the X-energy reactor, their control rods, if I go back to this page, the control rods that go in here aren't full length. They don't go all the way to the bottom of the reactor. And that is, again, to reduce their height. It's to try and make these things, these tubes that contain the control rods, a little bit shorter. Now, what that means is that, in principle, their rods, if they overshot, would start to also have negative worth. You can keep inserting the rod beyond the point where it's fully inserted, and beyond a certain point, the worth will drop off again, and that's on that blue line. Now, it wouldn't be able to extend that far, but it is something to think about if the cable snapped, for example, and you accidentally dropped it into the core. And what we saw here is that with our telescoping rod, which is this orange line, the amount of worth in the control rod, i.e. its ability to shut down the reactor, kept increasing the more we inserted it. And therefore, we weren't seeing negative worth. We did manage to find a couple of edge cases where we could get a little bit of negative worth, but a very, very, very small amount, so not something that's too concerning. Another thing we need to think about is depletion of the control rod, and this is something that's in progress. But when we're using the telescoping rod, the outer ring of the control rod, so going back to this picture, this blue stage on the outside takes the brunt of the incoming neutrons because it's at the edge. So if you insert the control rod a little bit, which is how HDRs are operated, it will take more of the neutrons. That will mean that the worth will degrade a bit. And we do see that this leads to this outer stage, that this is the worth of the control rod over time, and the orange line here is this outer stage. The purple line is a reference non-telescopic control rod. We see it deplete something like 2-3 times as fast. That we have not yet got far enough to know how big a problem this is. Our next task is to understand realistic conditions for the control rod. So understand how much it's inserted and for how long, right? Because these rods are only partially inserted. We do in general find as well that because we're trying to jam so much worth into a small area, this thing that extends and contracts, that overall on average we're also losing more worth, not just in the outside stage. So where we got to with this, we got to a point where we think this can work from a neutronic perspective. We're just completing the analysis of how long it will last. We're currently doing wear testing of the control rod. We think that it's stable under oxidation, but we haven't yet confirmed that by continually inserting and retracting it, it could, in theory, wear away as the insertion and retraction happens. And so our next step there is we've got a machine that will insert and retract it a lot under high temperature conditions to check that it will still operate and it won't stick and it won't fall down. So that's the next thing we're doing, and we got another year and a half on this. Then the other thing we're doing is doing a more detailed cost-benefit analysis to try and get some more rigorous numbers as to how much we can save this way versus any costs associated with redoing design of bits of the plant. Okay, so that was my second topic, and I'm on to my third and final one. So I just want to talk a little bit about some of the work we're doing on fusion blankets. So fusion system, you have a plasma in the middle, and most of them have deuterium and tritium that react in the middle of the plasma, and that produces neutrons that come out, and those neutrons get soaked up in a material called a blanket. And that blanket serves a couple of functions. It firstly has got to take the heat away, a bit like the coolant in a fission reactor. And it also needs to breed more tritium. You have to use the blanket to produce the tritium that you need to do the reaction in the first place. Otherwise, you'll run out of tritium really quickly. Now, the balance of neutrons in a fusion system is really quite delicate because every DT reaction in the plasma produces one neutron. And if you were to just absorb the neutron in the lithium, then you would only get one tritium back for every neutron. So you could end up in a situation where you needed it to be perfect, and it would never be perfect. You would always lose some neutrons to the environment out the sides, absorbed in structural materials, etc. Now, one way of getting around this is to include a material called a multiplier, which is a material that has an N2N reaction. So one neutron hits something and two N come out. Another way, as you all know, you could do this is to put some uranium in there, and then you could get fission going and you get lots of neutrons. But fusion people don't want to do that because they want to keep fissile material away from their nice clean device. So you use materials that have this reaction in them. And a parameter that fusion people really care about is the tritium breeding ratio, and that's how much tritium you get for every tritium you put in. So a tritium breeding ratio of 1 means 1 tritium out for every tritium in. Now, there's a few other things you need to worry about in the whole fusion system that mean that a tritium breeding ratio of 1 isn't good enough. Tritium decays with a half-life of about 13 years, so you will lose some of it while recycling it. The other thing is your systems that extract it will never be 100% efficient because tritium is fundamentally an isotope of hydrogen, it's leaky, it absorbs in everything. So getting all your tritium is tricky. So that means you need to breed more tritium than you consume in the blanket. Now, one choice of blanket material for a molten salt reactor is FLEBE, which is a lithium fluoride, beryllium fluoride salt. That's very attractive because it contains both lithium and beryllium. It's also of interest for use in fission reactors, for example, the Kairos system. It has a low electrical conductivity, and that's a really useful property in a fusion system because if you start pumping a electrically conducting fluid around the magnetic field, you will have problems. And it also operates at low pressure. Now, there's two important challenges on this. One of them is that the tritium breeding ratio for FLEBE is inherently quite marginal. It's quite difficult to get this system to breed enough neutrons, so breed enough tritium once you've taken into account all these losses. I believe the industry thinks it can be done. It's just challenging. The second is that FLEBE melts at 459 C. The current generation of fusion structural materials can only get up to 550 C. And you need some margin here against freezing. So this is probably too small a margin. So one of the things we are looking at is, can we find a molten salt that drops this melting point while keeping a tritium breeding ratio that's high enough? And we could, in principle, switch to a chloride salt. So chlorides have lower melting temperatures. Now, FLEBE has long been considered the best breeder for molten salts. And that's driven by neutronic analysis that was performed decades ago. Now, part of that comes from natural chlorine is a mix of chlorine 37, which is 25% of it, and then the rest of it's chlorine 35. Chlorine-35 is quite a nasty neutron absorber, and so as soon as you start putting that in your system, you're going to have problems. But modern nuclear data evaluations predict that this one has a non-trivial end-to-end reaction. So in principle, if you can enrich chlorine in chlorine-37, then chlorine-37 isn't a bad thing to put inside a fusion system from a neutronic point of view. Enriching chlorine probably isn't as hard as it sounds. Chlorine's a gas, so enriching things that are gases is doable. You do have to worry about chlorine going around as a Cl2 molecule, which means you have one of these can be paired with one of these, and that makes enriching it a bit trickier. It's also something the fission industry probably needs. So there's interest in fission chloride reactors, again by TerraPower, and that may well solve that problem. So for sort of speculative research as we're doing in a university, this doesn't feel an unreasonable thing to think about. So what we're doing here is just a proof of concept of can this in particular work. So we took a sort of quite a simple model of a tokamak and set up a model to understand the breeding ratio of a chloride-based salt. And we're comparing it to Phlebe as a base case. And what we found is that chlorides, if we enriched in chlorine-37, can slightly outperform Phlebe. Now, depending on what you do with this, if you start getting fancy and putting other materials in there to try and breed additional neutrons, so for example, if you put layers of solid beryllium inside of this system, this advantage could get eroded, but it's certainly at the same sort of level, if not slightly better than you could do with Phlebe. Again, based on enriching the chlorine and based on what we now know about nuclear data. Now, there are challenges that remain. So one of the big ones with using chlorine in a system is that if you breed any chlorine-36, that's a long-lived radioisotope, and we never want those, but fusion people are particularly precious about not having chlorine-30, too much long-lived waste in their system. It is not clear if this would be enough of a problem to avoid producing high-level waste. It's on the border of acceptability. The other thing is that you can end up getting slightly more damage to your structural materials and you might need slightly more shielding, and that's because you get less downscatter of neutrons, so it produces more high-energy neutrons will get through the blanket. And finally, corrosion can be an issue with chloride salts. But one of the advantages here is back to our temperatures, our melt temperatures are now low enough that you can imagine pairing this with existing steels. So while you still have a pretty big corrosion challenge to get around, it's perhaps a challenge that might turn out to be easier or at least a good fallback position when trying to find a more exotic structural material to pair with Phlebe. So where we got to in conclusion is this is a potential route to get inside of the envelope for what's called Ratham steel, which is the fusion industry known steels. You can, in principle, get a little better breeding ratio as well. General problems here are technology readiness, enrichment in chlorine, and waste disposal. So it's a potential fallback option. No one's willing to pay me any money for future work right now, which is very sad. We'll keep asking the DOE. But in principle, if we were to get money, or like, I don't know, free graduate students or something, we would need to understand the properties of this material better. We would need to do more detailed neutronic modeling, corrosion testing, thermodynamic testing to find the material properties, nuclear data. These are all sorts of things that could be looked at. So yeah, that's all I have got. Thank you all for attending this. I know I am not quite the thing standing between you and break, but this is at least the last seminar. Some acknowledgements to funding where we've received it, and also to the many, many people who have helped with putting this together, including my collaborators and some students. And Merry Christmas.
Then we had some skewness in power from the bottom levels to the top ones. Would it make sense that we could get like some more control rod work if we inserted the rods from the side, right?
So let's pull back to a diagram of this so we can see what we're looking at. Is that the best one? Yes, it's probably the best one. So we're looking at this thing on here. So yeah, you're saying if you bring control rods this way, it's an interesting idea. I mean, the first thing from our perspective is we're trying to stay as close as possible to what's already been done, right? Because they're trying to build these reactors. But that doesn't mean we shouldn't look at other things. I'd say you might gain worth this way by sticking them, you have more worth wrapping around the core. You might lose a little bit from, because unless you had these like at every height increment all the way up the core. So again, my diagram's a bit off screen, but if you had them at every height increment, then you might get enough work, but if you started leaving gaps, that could give you struggles to get a shutdown worth. Nonetheless, doing it that way also knocks height off the system. So yeah, it's well worth looking at. Yeah, good idea.
So still on the topic, I don't know like how much detail you're allowed to go into about your prototype, but what is the internal mechanism that is letting those rods like extend and retract?
Right, okay, so let me find, this is probably best diagram. So the way the existing rod works is you've got a tube and you have a cable that goes through the tube and it's attached to the bottom of it. And then the whole thing's hanging on the gravity, right? And so if you release the cable, then the rod will drop. So if this is my control rod, it's as much as I pull it, it will come back. Now, the idea with this is that there's two ways you could do it. One of them is, well, there's three ways you could do it, and we considered them all. One of them is to hold each stage with its own cable. The other one is to have a system with quite a lot of friction in it, so that you have these two flanges here, and if you pull this one, it would gradually pull on this one. And if you did that, then the smallest stage would stick out the bottom, and every stage would be as high as it could, right? Potentially. But you might have problems where if you pulled it versus if you pushed it, the stages could be in different places and you might get more wear. So what we end up with is having this being free, essentially. So these flanges, so in each of these tubes, there are, on the outside of the tube, there is like a sticky out, oh, I can't think of the word, a sticky out bit. Let's go with that. And then there's a groove on the inside of the one outside it. So there's like a little ball, it's like spherical sticky out bit on these things, and it travels inside of this groove, and there are 3 grooves. And 3 is chosen particularly because that's one way of mounting something so it doesn't rattle, but it's not over constrained. So that's a long way of saying that they will all fall as far as they can get to. And eventually they'll be stopped because this thing will hit that thing and that thing will hit that thing. And then it extends like this. So every stage falls as far as it can. You only hold it in the middle of the inner stage, and then that's pulled by a cable up to the top, and the longer it goes, then the further it extends.
Them getting stuck, and you don't want them to get stuck for obvious reasons. So do these require power to move? And if yes, what happens if you have an accident scenario that no longer allows power to operate these? Will they fully extend if there's no power?
Right, that is a very good question, right? So the idea in principle is it's the same mechanism as the existing control rod. Hold the bottom with a cable. The cable is held by whatever mechanism the cable is held by, and then typically with these things, they fall under gravity, right? So if you lose power, then it releases something that then slams the control rod in. Same as an existing reactor. So far, so good, right? Biggest problem with this is proving that it won't stick, right? Because if it sticks and you drop in, it doesn't fall in, you've got a big problem. And when I spoke to someone who worked as the utility in the PWRs, just as a chat, and we were talking about this idea, he said that would be what scared him, right? What if it sticks? Now, there are a few other things you need to worry about, which are if you were to drop it and there's nothing if you do nothing and you take this thing and you drop it, you could imagine the whole thing collapsing to the bottom of the core down here, right? And that's as bad as it's sticking because the whole thing is just down here and it's not up here where you need the work. Now, you can get around that in many different ways. So one way you get around it is by having flanges. So make this flange overlap the top of the hole so it doesn't fit. The other thing you can do is mess with the hole. So you can imagine having the hole become thinner and thinner as you go down, and then it can't collapse on the way in. So that one we think we can get around. And the third thing you need to worry about is what happens if you accidentally got it pushed out of the core by some sort of pressure transient. And the way we have that is if it's hollow, then it means the pressure is equalized through it. So again, a long way of saying the main thing to do is prove it won't stick. That probably means having pretty decent tolerances on all of these grooves so that it's not it's got plenty of room for maneuver, but that could cause a problem where it rattles and sways. And if it rattles too much, you can imagine this bending and hitting the side of the tube, and that would be bad. Now, from this picture, it looks like it could never hit the side of a tube, right? But this thing in real life is, oh, I want to say about 5 centimeters radius or diameter, something like that, and 8 meters long. And each stage is 3 meters long. So yeah, if it rattles too much, it could get stuck on the side of a tube. All of the, so probably not thermal expansion, but either corrosion building up like layers of oxide layers on the surface, or some sort of corrosion layer that changes the properties of the surface, or it getting stuck because of some sort of tolerance issue. Either of those things would be plausible. Right, I think that where a lot of the PWRs sit is that they have a few percent before they start hitting some major upgrade, and a lot of them have found most of their way through those percent. So I think they've only got, it varies depending on the plant, but I think when you're talking about 1s and 2%, that's often something that is squeezed out of plants without really changing a whole lot. If you start going up to 5, 10, 15, 20%, that's where you start replacing plant equipment. It has been done. So if you look at BWRs, a lot of BWRs have received power updates. It uprates in the neighborhood of 15% by turning it off and then doing and moving some equipment around. And the utilities are seriously considering it as things stand.
On the topic of the irregular pin placement WR samples, does that pin placement like modify control rod work or the actual spider itself? Because I can imagine there's like spatial shielding effects from adding pins there.
That is something that we needed to check. Yes, so I didn't have a slide for it. I'll just pull the slide so that people can see what we're talking about. Yeah, so if we're doing this, our pins are in different positions around the rod, and the pins are a little bit smaller and there's more of them. It does not have a significant effect on control rod worth, and we checked, and it's like within 1% or something, so it's the same. However, the thing that does have an effect is increasing the enrichment. So if you increase the enrichment above 5% in a PWR, which people want to do because they want to run their plants for longer before they refuel them, then that means that more U235s are gobbled up in, more neutrons are gobbled up by U235 fission, and that means you have less thermal neutrons, which means that you have less control rod worth, which you will either have learned or will be learning in Professor Novak's class, which apparently runs in the spring. So now that's a problem that any PWR that wants to increase enrichment has. They have to check they have enough control rod worth to do it. Now, why is that relevant for this? If you increase the power coming out of the core, you don't want to compromise on cycle length, and you probably don't want to change the number of batches of fuel that you have. And if you don't know why that's important, you need to go back to Professor Novak's class again. And that means that you probably want to increase the enrichment above 5%, which means you're probably going to degrade control rod worth. But I should say that a lot of PWRs have margin in them. So like that most of them aren't up against the limit on shutdown margin or control rod worth. And they're sort of over conservative. BWRs, they tend to be designed to the limit. Question? Cool.
How about the thing of the thinness of the cladding?
So the control rod here is the same, but the fuel pin. Okay, yes. So good question. So in principle, you could probably reduce the fuel cladding in proportional to the size of the pin, because the pressure in the fuel pin would reduce in proportion to the radius. So you could make the clad proportionally thinner. And these aren't that much thinner, right? They're a little bit thinner. However, if you needed to keep, so I have all these letters on here and I didn't explain what they are, which is terrible presentation practice. Don't do this. When you do your thesis defenses, don't do this. So if you do have a case with this, if you drop the thickness of the clad a little bit because so if you increase the thickness of the sorry. If you keep the same cloud thickness, that means you've dropped the amount of fuel you've got a little bit. And that would drop you from this orange line to this pink line here. Right? So it will drop your cycle length by a tiny amount, which is still important. So again, it means you might need to enrich a little bit more against it. Hang on, sorry, I'm comparing with the wrong lines there. It's not that one. It's the difference between the blue and the pink line, so which you can barely see, right? So these two lines have different cloud thicknesses, and they almost overlap, but they start to depart down here because one of them's got less fuel in it. So yes, it does make a small effect. Yeah.
Sure you thought about control drums. So in space reactors,
Yep.
instead of having something around the edges of this graphite, we have drums that rotate in for absorption and rotate out for reflection. Why have you rejected this as an option instead of gone with telescoping?
Right, so for us, it was trying to stay as close as possible to what X Energy or the HTR vendors are already doing. So that means staying with a control rod. I believe, but I don't know, this is something I heard anecdotally, and maybe you can correct me if I'm wrong, if you start trying to have a control drum that goes 8 meters tall, that might be straining the limits of what you can do with the drum, or maybe it's difficult to design mechanically, but I'm not sure. Tim Grunlow was telling me earlier today, Dr. Grunlow, that apparently the venture capital firms are desperate for new nuclear startups, so maybe we could start one and do that.
Interested in the thermal analysis you did for the reorganization of the pins. Did you look at the temperature in the fuel or just the coolant?
Just the coolant, and the reason is that from so the power in suppose you uprated the assembly in proportion to the number of pins, right? Then each pin has the same power as the reference assembly. So one of these pins has the same power as one of those. And the boundary condition is almost the same, right? We have the same coolant temperature. So if the boundary condition is the same, then the temperature in the pin should be the same by virtue of the power being the same, even though the radius is a bit smaller. I know that's not a perfect correlation, but it's pretty close. Yeah. That's a good point. Yeah. Yeah, that's a good point. And understanding the temperature of the outside with a CFD calculation, that'd be a really cool thing to do. That's a good idea. I would say one of the things here is to try and understand how close you can put these things. And the way this is designed as it stands is to keep a minimum distance between pins of 2 millimeters. And that number comes from, oh God, probably spacer grids. There was a reason, but I can't remember what the reason was. Yes, yeah. So somehow that's going to drive how close you can get pins together. This has pins that go closer to the guide tubes than 2 millimeters, because this one has pins that go closer to the guide tubes than 2 millimeters as well. I do not know how close those can go before that becomes limiting. So that's a big question as to the manufacturing detail. Yeah.
Did you also look at things like the flow profiles and turbulence that this might cause?
No, and that would be a very important thing to do, again, in relation to Dr. Novak's point as well, is to, if you had a spacer grid design for this, you would want to, do CFD analysis of it to understand all of that, and then also do bundle testing on it as well to work all those things out. I'm trying to get enough information out of the fuel vendors from the goodness of their hearts to tell me what is and isn't possible, but designing the spacer grids to manage turbulent heat transfer here is something that all fuel assemblies have to do and would need to be done for HIS as well. Yeah. I guess indirectly. So if we look at, let me see which one to go to first. The easiest one's probably telescoping thing. The big problem here is you want to get your reactor through 20 years before maintaining it, right? So this is an online. If it's a prismatic reactor, like for example the UIUC microreactor project, then it probably shouldn't make much difference because you could always replace the control rod. That's a bit more expense from replacing the control rod, and it's a capital cost. So it's a material cost, but material costs probably aren't that much. If it's the X-Energy system, they would like to be able to operate this for 20 years without ever taking it offline, which is challenging for a reactor that's never been built, right? Or a first of a kind. But if you can do that, then that means your control rod has to last that length of time too. And the control rods are slightly inserted at power down to about here to control the power distribution. And if that degrades the control rod enough that you have to replace it, which it might, we haven't done the analysis yet, then that will be limiting on the replacement time, which would affect maintenance. I'd say that all of it's wrapped together with PWRs because you want, at the moment they're run for 18 months between maintenance cycles. The operators would like to take them to 2 years. They'd also like to uprate them, all of these, and then if you start bringing more power into them and then also wanting to extend the runtime, then that increases, limits associated with when you have to do maintenance.
I think we have time for one more really quick question. Let's thank our speaker for this.